Hello dear students, today we are going to discuss about a small topic in electrostatics, which is electric field due to a uniformly charged rod. Actually continuous charge distributions. So continuous charge distributions we use integration method to find out the electric field. So let us suppose a charged rod having positive charge and having length capital L. L is the length of the rod. Our aim is to calculate electric field at a point P, which is at a distance small r from the edge of the charged rod. So our aim is to calculate the electric field at a point P, and given linear charge density is lambda. Linear charge density means charge per unit length. Total charge by total length is nothing but linear charge density, that is represented with a letter lambda, and our aim is to calculate the electric field here. Initially we calculate the electric field along axial line, later we discuss about the next cases. So during the continuous charge distributions, every time we take a small factor in the material, so that here material rod we take a small factor, that is dx. Here dx is the small element. So initially we take a small element, with respect to the small element we identify the electric field here, that is small electric field, and then we integrate that electric field to the given limits. Okay, so dx is the small element which is at a distance x from point P, let us suppose. So the electric field with respect to the component dx, having charge dq, let us suppose. So what is the charge density? Charge density lambda is equal to dq by dl, charge per unit length. So dq by dx. So dq is equal to lambda into dx. Here we take the small factor dx, so that lambda is equal to dq by dx and dq is equal to lambda into dx. And then electric field E is equal to dE, small electric field. We are going to calculate small electric field initially, then we integrate. So small electric field dE is equal to k into, k is 1 by 4 pi epsilon naught, generally we termed it as k, into q means dq, by the dq charge is at a distance x from P, so that k into dq by x square, that is the small electric field with respect to the small element we choose, and we substitute the value of dq here, k into lambda dx by x square. So this is dE is equal to k into lambda dx by x square. Then by integrating on both sides, then integration of dE is equal to integral of k into lambda dx by x square. So integral of dE is equal to E. Okay, and next integration of k into lambda are the constants, so that take it out of integration, into dx by x square. So we need to write the integration limits here. So from where to where we are going to calculate the electric field? Our aim is to calculate the electric field due to the entire rod. So from the distance r to r plus L, r is from here to here and r plus L is from here to here. So our aim is to calculate for the total length, that is r to r plus L, the distance r to r plus L. R is, this is the point, r plus L is, this is the point. So we are integrating to the entire length of the rod. That is why we take the limits r to r plus r. Okay. So that is k lambda into integral of 1 by x square is equal to minus 1 by x. The limits are r to r plus L. So k lambda into, if you substitute the limits, then it is which is equal to 1 by r plus L. This is electric field, and finally the electric field value E is equal to k lambda into L by r into r plus L. This is the electric field due to a uniformly charged rod at a point on the axial line. We calculate the electric field due to a uniform charged rod along the axial line. Okay. So along axial line, its value is k lambda L by r into r plus L, where L is the length of the rod, r is the distance of the point where you want to measure the electric field from the edge of the rod. So finally that is the factor. Okay. Let us go to the next case. A charged rod. Our aim is to calculate the electric field at a point P perpendicular to the charged rod. This is the next case. One edge makes an angle theta 1, another edge is theta 2. Let us suppose the angle here theta 1 is in anticlockwise direction taken as positive, theta 1 is clockwise direction taken as positive, theta 2 is anticlockwise direction taken as negative. Okay. So let us suppose the rod having length L, and we choose a small length element initially. Initially we calculate the electric field at this point with respect to a small element dx. This small element is at a distance x from point A. Suppose this is point A. From here to the element, the distance is x, and with respect to the dx, the electric field at point P, which is called dE, the small electric field dE with respect to the small length element. And also we know lambda is equal to dq by dx. Linear charge density is lambda, so dq is equal to lambda dx, the small charge element, so that the dx length having the small charge dq. With respect to the small charge, we are going to calculate the electric field at a point P initially, that is dE. Later we will integrate to the total. Okay. So the value of dE is, this is the dE direction, and with respect to vertical it makes an angle theta. So the dE is divided into two components, dE sin theta and dE cos theta. So the dE cos theta is in vertical direction along y direction, let us suppose, dE sin theta is in x direction. So that dEy is equal to dE cos theta. So what is electric field E? Electric field is, if you want to calculate, if you calculate Ex and Ey, then electric field E is equal to root of Ex square plus Ey square. So our aim is to calculate the two components Ey and Ex. So let us, we are going to calculate the component Ey. So dEy is equal to dE cos theta. So dE means k into dq by distance. Here what is the distance? Here this is x, this is r. So the distance is r square plus x square. The distance is r square plus x square. So k into dq by root r square plus x square whole square, which is equal to r square plus x square. This is dE. And cos theta. This is angle theta. Cos theta is equal to adjacent side by hypotenuse. So r by r square plus x square whole power 1 by 2, that is cos theta. So dEy is equal to k into r into dq means lambda dx by r square plus x square whole power 3 by 2. Okay. Then we substitute the value of r here. From the triangle tan theta is equal to opposite side by adjacent side. Opposite side is x, adjacent side is r. So x is equal to r tan theta. So dx is equal to r secant square theta d theta. So we substitute in place of x r secant square theta d theta, in place of dx r secant square theta d theta, in place of x r tan theta. If you substitute these two factors, then dy is equal to k into lambda into r into dx. Dx is r secant square theta d theta by, already here we have r, so r into r square secant square theta d theta by r square plus x square, x is r tan theta, r square tan square theta whole power 3 by 2. Okay. So that is dEy. So dEy is k lambda by r finally into cos theta d theta. This is the final relation. Dey is equal to k lambda by r into cos theta d theta. So we calculate the small electric field with respect to the small length element. So we are going to integrate that electric field value with the given limits. So by integrating on both sides, dEy is equal to k lambda by r into integral of cos theta d theta. Here the limits is minus theta 2 to theta 1. Those are the limits. So Ey is equal to k lambda by r into, this is sin theta, the limits are minus theta 2 to theta 1. So finally we get Ey is equal to k lambda by r into sin theta 1 plus sin theta 2. This is the y component of electric field with respect to the uniformly charged rod. Okay. Similarly, if you calculate the x component, see, if you calculate the x component, the only difference is in place of cos theta we write sin theta. So along x direction, this is Ey, along x direction if you calculate, along x direction, see, dEx is equal to dE sin theta. Okay. So dE is equal to k into dq. dq is equal to lambda into dx by r square plus x square into sin theta. Sin theta, here sin theta is opposite side by hypotenuse. So x by r square plus x square whole power 3 by 2. That is dEx. So that is dEx is equal to k into lambda into x dx by k into lambda into x dx by r square plus x square into r square plus x square whole power 1 by 2. Sorry, here 1 by 2. So if you multiply r square plus x square whole power 3 by 2. So by substituting dx is equal to r secant square theta d theta, dEx is equal to k lambda into r secant square theta d theta into dx by r square plus x square whole power 3 by 2. So if you substitute r secant square theta in place of x, r square tan square theta, then finally we get a relation which is equal to k lambda by r into sin theta d theta. This is dEx k lambda by r into sin theta d theta, because secant square theta there is cancelled, r square tan square theta, that is secant square theta is cancelled, and finally in place of x here k lambda into x dx, here x is equal to x factor also there, k lambda into x into r secant square theta d theta dx. So dx is equal to k lambda by r into sin theta d theta. So if you integrate that factor, you can get electric field along x direction. So by integrating, integral of dx is equal to integral of k lambda by r into sin theta d theta. The limits are minus theta 2 to theta 1. So Ex is equal to finally k lambda by r into, if you integrate, that is minus cos theta, limits are minus theta 2 to theta 1. So Ex is equal to, x component of electric field is k lambda by r into cos theta 2 minus cos theta 1. So this is x component of electric field. Okay students, and this is about the electric field values along y and x directions. Then if you want to calculate the resultant electric field, what is the relation? The resultant electric field is equal to root over Ex square plus Ey square. So we calculate the value of Ex and Ey. If you substitute these two values, it is possible to calculate the resultant electric field with respect to a uniform rod at any perpendicular point P. Okay. So let us discuss about the various cases in this point. Let us discuss about the various cases. So we get Ex and Ey values. Once again we write here, Ex is equal to k lambda by r into cos theta 2 minus cos theta 1. Similarly Ey is equal to k lambda by r into sin theta 1 plus sin theta 2. These are the two relations we get, and if suppose the two values are same, theta 1 theta 2 both are equal, that is on the equatorial line. On equatorial line, if you want to calculate electric field on equatorial line at a point, then theta 1 is equal to theta 2, which is equal to theta. Let us suppose theta 1 is equal to theta 2. So Ex is equal to 0, because cos theta 1 minus cos theta 1, that is 0. And Ey is equal to k lambda by r into sin theta 1 plus sin theta 1, that is 2 sin theta 1. So that is 2 sin theta. So Ey is equal to 2 k lambda by r into sin theta. This is the electric field along y direction. This is electric field along x direction. So with respect to these two values, it is possible to calculate the total electric field. Okay, this is on equatorial line. For example, semi-infinite wire. Semi-infinite wire means, suppose if you take this is semi-infinite rod. If you want to calculate the point P is here, if you want to calculate the electric field here, and the rod is infinite, the length of the rod is infinite length. In this case, the theta 1 is 90 degrees, but theta 2 is 0 degrees. Theta 2 is 0 degrees because the point lies at one end above the edge, so that theta 1 is 90 and theta 2 is 0. In this case, the electric field values Ex is equal to theta 1 90 and theta 2 0. So cos 0 minus cos 90. So that is k lambda by r into cos 0 minus cos 90. So cos 0 is 1, cos 90 0. So Ex is equal to k lambda by r, that is Ex. Next Ey. If you calculate, Ey is equal to k lambda by r into sin theta 1 plus sin theta 2. Sin theta 1 plus sin theta 2. Here theta 1 is 90 degrees. So sin 90 plus sin 0. So the Ey value also k lambda by r. So in this case, in case of semi-infinite wire, this is semi-infinite wire. In case of semi-infinite wire, this is the relation of Ex and Ey. Then total electric field is root Ex square plus Ey square. In case of infinite wire, suppose if you take infinite wire, in that case infinite charged rod, so here this is infinite charged rod. In this case theta 1 is equal to 90, theta 2 also 90, because the rod having infinite length, on the both edges it is having infinite length. The rod having infinite length, so the angles are 90 and this is also 90. So theta 1, theta 2 both are 90 in case of infinite length rod. So that Ex is equal to, substitute in place of theta 2 and theta 1, 90 k lambda by r into cos 90 minus cos 90. Cos 90 is 0. So Ex is equal to 0 and Ey is equal to k lambda by r into sin 90 plus sin 90. So Ey is equal to 2k lambda by r. Okay students, so this is about today class, and we are going to discuss about the applications related to the class later. So this is the electric field due to a uniformly charged rod. In the first case we calculate the electric field along axial line, and in the second case we calculate electric field due to a uniformly charged rod perpendicular to the charged rod at a point P, and their electric field is divided into two components, Ex and Ey. So we calculate Ex and Ey. So Ex and Ey components are here. So based on the angles, based on the different cases, the theta 1, theta 2 values will depend. If theta 1 and theta 2 are equal, that is equatorial line. If theta 1 is 90 degrees, theta 2 is 0 degrees, that is semi-infinite wire. If both angles are 90 degrees, then it is infinite wire. In the three cases also we discuss here the values of Ex and Ey. Okay students, let us go to the problems, and later we will go to the next concept. Okay students, let us discuss the example related to the concept we discussed. Suppose this is a charged wire having length L and linear charge density lambda, and we are going to find out the electric field at a distance r from the horizontal line, a perpendicular distance r from the horizontal line. So what is the electric field at a point P with respect to the rod we consider here? So Ex and Ey components, Ex is equal to, we know, k lambda by r into cos theta 2 minus cos theta 1, and similarly Ey is equal to k lambda by r into sin theta 1 plus sin theta 2. So here theta 1 and theta 2 we need to identify here. So theta 1 is the angle, one edge, left edge angle theta 1 is 60 degrees, and right edge angle theta 2 is minus 30 degrees. Here we take theta 2 is negative. Why it is negative? Because in our derivation we take theta 2 as anti-clockwise angle, but that at 30 degrees here is located like a clockwise angle. So we take in previous derivation the angle theta 2 is an anti-clockwise angle. That's why in the derivation we take theta 2 negative. We made it the correction here. That's why theta 2 is equal to minus 30. So if you substitute k lambda by r into cos theta 2 minus cos theta 2 minus 30 minus cos 60. So cos 30 is equal to root 3 by k lambda by r into minus root 3 by 2 plus minus 1 by 2. So finally Ex is equal to minus of k lambda by r into root 3 plus 1 by 2. This is Ex value. Similarly we calculate Ey. Ey is equal to k lambda by r into sin theta 1 plus sin theta 2. So sin 60 plus sin 30 minus sin 30. So k lambda by r into sin 60 is root 3 by 2 minus 1 by 2. So that is root 3 minus 1 by 2. This is Ey. So that is Ex and this is Ey. So if you got Ex and Ey means what is E? E is equal to root Ex square plus Ey square. That is the result. Okay students. So if you consider the point which is here and which is the right side of the right side edge, and in this case if you take a clockwise angle also it is not a problem, but you need to identify the sign convention here. Whatever the derivation we did previous, the sign according to sign conventions we take theta 2 as negative, but here theta 2 is positive. So that's why in the derivation we take theta 2 negative. Again we will make it correct, that is theta 2 is equal to minus 30. So that finally we get the relations. Okay, let us go to the next problem. Okay students, see this problem. Our aim is to calculate the electric field at a point P with respect to the wire, with respect to the rod. So Ex is equal to, we know k lambda by r, the distance here is r, into cos theta 2 minus cos theta 1. Here theta 1 is 30 degrees, theta 2 is 60 degrees. Here no need to take sign convention because already we took in the derivation. So that theta 2 is equal to positive, theta 1 is equal to 30 degrees. Okay, these two are positive values. So k lambda by r into cos theta 2 cos 60 minus cos 30. So k lambda by r into cos 60 minus cos 60 is 1 by 2 minus root 3 by 2. So 1 minus root 3 by 2, this is Ex, x component of electric field with respect to the rod. Similarly y component of electric field Ey is equal to k lambda by r into sin theta 1 plus sin theta 2. So y component of electric field Ey is equal to k lambda by r into sin theta 1 is 30 plus sin 60. So y component of electric field is equal to k lambda by r into sin 30 1 by 2 plus root 3 by 2. So finally 1 plus root 3 by 2, that is Ey. Okay. So Ex and Ey we get finally E is equal to root Ex square plus Ey square. Okay, hope you understand the topic what we are discussed today, and we gave 2 examples related to the topic also, and it's not a difficult thing, any topic, if you understand in a proper way. Thank you very much. We will meet in the next class.